Итак, Kip Thorne.
Говорит по-русски, но я не могу. Знаю только 100 слов, и поэтому надо говорить по-английски. Извините, пожалуйста. $1.3 billion years ago, when here on Earth the first multicelled forms of life were arising from evolution and spreading over the Earth. But in a galaxy far, far away, two black holes traveled around each other. And here I show you what they look like as seen by your eyes if you were near them. What you see is the shadow of the black holes against the stars that are behind the black holes. They create a wonderful pattern through a process called gravitational lensing. They bend the light rays that travel around them, and the bending of light rays creates these beautiful patterns. These black holes traveled around each other, spiraling together and collided and merged. And as they merged, they produced a giant burst of gravitational waves. These waves traveled outward from the galaxy in which the black holes live. They traveled into intergalactic space. They traveled across the space between the galaxies, a distance of 1.3 billion light years. And 50,000 years ago, they arrived at the edge of our galaxy. That was when our ancestors were sharing the Earth with the Neanderthals. For 50,000 years, they traveled through our galaxy until they reached the Earth. Those problems. One moment, I need to, okay, until they reached the Earth. They reached the Earth initially up at the Antarctic Peninsula. They traveled through the Earth, unscathed, unaffected by all the matter in the Earth, upward until they arrived at the LIGO gravitational wave detector in Hanford, Washington, in North America, and then or in Louisiana in North America, and then 7 milliseconds later, they arrived at the LIGO gravitational wave detector in Hanford, Washington. The signals were recorded automatically by a computer, and the computer produced a web page which was broadcast to the members of the LIGO scientific collaboration, a collaboration that included 1,000 scientists around the world, including some from what is called the Virgo collaboration in Western Europe. These are photographs of some of the members of the collaboration. These 1,000 scientists, of whom I am one, studied the signal very carefully. The instrument was very complicated. There were 80,000, nearly 100,000 data channels telling what was going on with the instrument and with the environment, so that you could tell whether or not something was wrong in the instrument. And that's how complicated these instruments were. And after 5 months of studying these data channels to be sure nothing was wrong, and of analyzing the data, the result was announced at a press conference in Washington, D.C., at which I and 3 other colleagues spoke. And it made the headlines in newspapers around the world, here in Vienna, Austria, the New York Times, that gravitational waves had been discovered. Now, how did we get there? How did we come to have these detectors and make this discovery? So I will tell you the history, from a brief version of the history from my personal point of view. It begins, of course, with Albert Einstein. 100 years ago, in 1916, Albert Einstein used the equations of his general relativity theory to predict that gravitational waves exist. The waves that he predicted stretch space back and forth in one direction, squeeze it in the orthogonal direction as the waves propagate toward you, as shown here. The farther apart two points are in space, the larger their motion. The thing that is constant is the ratio of the magnitude of motion divided by the distance between the 2 points. So that motion was very, very small for these signals. In LIGO, there were mirrors that were hanging from overhead supports 4 kilometers apart. And they were sitting on, moving with the stretching and squeezing space. And their motion was 1/100th the diameter of the nucleus of an atom. A tiny, tiny motion. I will explain that a little more in a few minutes. In his classic paper in 1916, Albert Einstein said, in effect, I don't think these waves will ever be detected because they're far, far too weak. However, approximately 50 years later, in the 1960s, Joseph Weber, a physicist at the University of Maryland in North America, built the first gravitational wave detectors. He was the first person with the courage to believe that he might be able to detect gravitational waves. And the reason he had courage was that we had great new developments experimentally, the laser, for example, and computers that Einstein had never envisioned. And we understood that there were objects like black holes and neutron stars that would produce gravitational waves much stronger than anything that Einstein had ever conceived of. In 1966, let me back up. In 1963, I met Joseph Weber at a summer school in the French Alps. We went hiking together. I listened to him lecture, and I got very excited about gravitational waves. And so, in 1966, when I had completed my graduate studies, I had my PhD, I went to Caltech in Pasadena, California, as a young professor. And I decided to create a research group working on black holes, neutron stars, and gravitational waves, a theory research group. And in 1968, I made my first trip to Moscow. And I came here to Moscow State University to the physics faculty, and there, Yakov Borisovich Zeldovich, one of the truly great astrophysicists of all history of humanity, introduced me to Vladimir Virginsky. And I became close friends with Virginsky, with Vladimir Borisovich Virginsky, or Volodya as I call him in my informal American way. I, as a theorist, and he as an experimenter, had very good communication, and we actually began to collaborate together. In 1969, Weber announced evidence that he may have discovered gravitational waves. Virginsky and his research group, including Valery Mitrofanov, who is here with us today, sadly, Vladimir Borisovich Virginsky died earlier this year. But Virginsky, Mitrofanov, and others in the research group replicated the experiment with a better detector and saw no gravitational waves. It took experimenters in the West one more year for any of the other competitors to test this. They also saw no gravitational waves. And so then the question was, what next? Well, I was convinced, independent of whether waves had been seen, that they would be tremendously important for science, for our understanding of the universe. And so I wrote first of a series of articles with one of my students, William Press, in 1972, laying out a vision for the science that could be done with gravitational waves. To me, The contrast, the difference between gravitational waves and electromagnetic waves was very important. Electromagnetic waves are oscillations of the electric and magnetic fields that travel through space and time. Whereas gravitational waves are very different. They are oscillations of the fabric, the shape of space and time itself. Electromagnetic waves from astrophysical sources are almost always incoherent superpositions of waves emitted by particles, atoms, molecules, whereas gravitational waves are emitted coherently by large amounts of mass or energy moving in a highly dynamical manner. Completely different way of producing the waves. Electromagnetic waves are easily absorbed and scattered, much too easily, as they travel through space. They are absorbed and scattered by dust. Of course, they cannot propagate to the Earth. Gravitational waves are never significantly absorbed or scattered. Even waves that are created at the birth of the universe and travel through the hot, dense matter of the earliest universe are not absorbed or scattered. So these waves are the ideal tool for exploring, for example, the birth of the universe, to which I will return later. With these differences being so great, it seemed obvious to me in 1972 that many gravitational wave sources would never be seen electromagnetically. And in fact, that was the case with the gravitational waves from the colliding black hole that we discovered. They were very bright in a certain sense that I will return to. Very bright in gravitational waves, but there was no light, no X-rays, no radio waves. It was only gravitational waves. On the other hand, there would surely be many sources that you would see both with gravitational waves and with electromagnetic waves. So this would be a wonderful tool for exploring both unknown parts of the universe and getting a deeper understanding of known parts of the universe that were already partly known. And the differences were so great that huge surprises were very likely. Every time a new kind of radiation has been used to study the universe, radio waves or X-rays, for example, there were huge surprises. The universe looked very calm, quiescent, not violent, seen through light. But when radio waves started to be used for astronomy in the 1950s and 60s, the universe looked violent. It was a huge surprise how different it was. And similarly, gravitational waves will bring us some very big surprises. So to me, in 1972, this was perhaps the most interesting and important thing I could do with my career, was to help the experimenters to detect gravitational waves, if I could. But first I had to be convinced that they had a good possibility to be successful. And that was not obvious. That same year, 1972, Rainer Weiss had recently moved to MIT as a young professor. We knew each other at Princeton. He was a postdoctoral student, I was a graduate student. He was an experimenter, I was a theorist. But we were friends. He moved to MIT, I moved to Caltech. In 1972, he developed an idea for a new kind of gravitational wave detector. The seeds for the idea, the basic underlying idea, was actually invented 10 years earlier here in Russia by Michael Gerstenstein and Ladislav Pustovoy. But the difference was that Weiss, who invented it independently, did not see the work of Gerstenstein and Pustovoy. Weiss was able, as a highly skilled and trained experimenter, whereas Gerstenstein and Pustovoy were theorists, Weiss was able to identify all of the major sources of noise that this instrument would face and figure out ways to deal with each of them and then compute how sensitive the instrument would be, compare with the strengths of the wave that I and other theorists were predicting, and conclude that if you made these detectors big enough, several kilometers inside, then you would have a good chance to detect the waves. His basic idea was if you hang 4 mirrors from overhead supports by wires, the gravitational wave pushes these mirrors apart as it stretches space in this direction, pushes these together as it squeezes space. Then half a cycle of waves later, it pushes these apart, pushes these together, and you use a technique called laser interferometry to monitor that changing difference in the arm length, changing difference between this distance and that distance. I heard about this. I had not yet seen what the paper that Ray Weiss had written, but I heard about it when I was just finishing writing a textbook that is called Gravitation that I co-authored with Carl Misner and John Wheeler. And I thought it was not an idea that would ever succeed, and so in the textbook I wrote that this is not promising. I regretted that ever since. I thought it was not promising, and then I spent most of my career helping to make it happen. So why did I think it was not promising? Let's consider how small the motion of these mirrors is. If I begin with 1 centimeter, I divide by 100, I get the thickness of a human hair. If I divide by 100 again, I get the wavelength of the light that is used in these interferometers to measure the motion of those mirrors. If I divide by 10,000, I get the diameter of an atom. If I divide by 100,000, I get the diameter of the nucleus of an atom. If I divide by 1,000 again, I get the mirror motions that I thought I have to try to measure. This is 1 trillionth, 10 to the minus 12 of the wavelength of light. And to imagine that you could measure the motion of mirrors to 10 to the minus 12 of the wavelength of light, in technical terms, to imagine you could split a fringe in an interference pattern to 10 to the minus 12 was incredible. And I thought it just was not plausible. Until I had extended discussions with Ray Weiss and with Vladimir Berdinsky. Over a period of several years, I studied Weiss's technical paper very carefully. I then became convinced, and then I decided that I needed to build a research group at Caltech to work closely with me. Berdinsky was too far away in Moscow, and I wanted to have a group of my own at Caltech, like the group at MIT, to build these gravitational wave detectors. And so my first step was to try and convince Vladimir Berdinsky to move to California. And he would not move. He would not leave his colleagues here in Moscow. His colleagues in his research group were more important to him than the lures of living close to Hollywood. And so he stayed, and I then made the next choice of bringing to Caltech Ronald Drever, an experimenter from Glasgow, Scotland, who had made some clever inventions that improved on Ray Weiss's design for these gravitational wave detectors. So Drever came to Caltech, and at Caltech then with financial support from the U.S. National Science Foundation, Drever and young colleagues built a 40-meter prototype gravity wave detector, 1% the size that we would ultimately need to have success. At the same time, at MIT, Ray Weiss finished a smaller prototype detector, got it operating, and more importantly, he carried out a feasibility study for these gravitational wave detectors with mirror separations of several kilometers. This study was done jointly with two companies, two industrial companies, and it included getting costs, finding out what the practical problems were in building such a device. With the results of the prototypes and this study in our hands, we felt we were ready to go forward, and so we jointly created in 1984 the LIGO project. It was a joint Caltech-MIT project with Weiss, Dreamer, and me leading the project jointly as a troika of leaders. Now, in that era, troika had some bad connotations. It sort of sounded like a leadership that was not very functional. It was always fighting. And that was a very accurate description. We were not able to be good leaders, and so after about 3 years, we gave up. And under encouragement from the National Science Foundation and encouragement from Caltech and MIT, we brought on a single person to lead this project. And this has been key, absolutely essential for the success of this effort. A project that involves 1,000 people, with each person working on some small piece of it. Everything must come together. You have to have one boss who makes wise decisions by consulting with the best scientists in the collaboration, but one person who's in charge. And this, in fact, is why we have succeeded, and our European colleagues in the LIGO project have not yet succeeded. They do not have a single boss who is really, truly in charge. This, by the way, was one of the pieces of advice that I got from Vladimir Virginsky. One boss. And so that's how it worked. In 1989, under the leadership of Robbie Volk, our new director, we put in a proposal to the National Science Foundation for LIGO. A proposal for a project that ultimately, by today, has cost more than $1 billion US. But the first step was going to cost about $300 million in the first phase. The facilities, we would first build facilities in which to put these detectors. This included large vacuum tubes down which the laser beams would travel, with 1.2 meter diameter vacuum tubes and 4 kilometers long, for example, and many other complicated facilities. Then we said we would build an initial set of interferometers. That's what we call our gravitational wave detectors, interferometers, that would be at a sensitivity where we probably would not see anything. And after getting experience with these first interferometers, we would then build advanced interferometers that were much more complicated, but much more sensitive, and those should have a high probability of success. We proposed this to the National Science Foundation. The National Science Foundation put us through a series of reviews by technical experts to determine were we really ready to do this. Did we have a good probability of success? Were our plans good? And after intense review for about 1 year, the National Science Foundation said, yes, we will ask Congress to bring us the money to pay for this. And so Volk, our leader, went to Congress to testify, asking for the money in Congress, the U.S. Congress. And to his surprise, powerful members of the astronomy community in the U.S. also went to Congress and testified against the project. To them, it was simply not reasonable to build a detector and see nothing, and then have to build a second detector before you had success. That culture was alien to astronomers, or at least to these particular astronomers. We had support from the astronomers of Caltech and many others, but these leaders of the astronomy community this just did not make sense. You could use this money to build a big optical telescope and immediately see wonderful things, and you don't have to build 2 generations. So we struggled for 2 years to get funded by Congress, and ultimately Congress gave us the funding. And from then until now, Congress has supported this project completely, never cutting our budget by large amounts. Whether the Republicans were in control or the Democrats were in control. And Congress, the U.S. Congress, takes great pride in the discovery that we have made. It's something that they and the American people and the people in, as I will explain, 15 other nations that contributed to this should be greatly proud of. In 1990, so then we brought on a new director, Barry Barish, who had experience directing big projects. And these directors were all from Caltech. And that was because Caltech was small enough that we could move very quickly in making something happen, whereas MIT was very big and very complex. And Ray could not get the support from MIT as an institution that was needed to get this project going. So we headquartered it at Caltech. Barry Barish then led us to construction of facilities from 1994 to 1999. In 1997, knowing that this was going to be, these instruments, these interferometers would be so complicated that it would require a very large team to build them, operate them, and do the data analysis. He expanded LIGO so that it included not just Caltech and MIT, and I should say Moscow State University, because Moscow State University joined with us in the late 1980s, Verginsky's group. It was the first group outside of Caltech and MIT that was part of this project. It included not just Caltech and MIT and Moscow State University, but also include now what have become 1,000 scientists and engineers at 80 universities and research institutes in 16 nations, including, of course, Russia, particularly with the Verginsky group. From 2000 to 2010, we built and operated the initial interferometers. As expected, we saw nothing. And that's what we had told Congress. We will probably see nothing, and Congress kept giving us the money we needed to move on then to the advanced interferometers. 2010 to 2015, under new leadership, because Barish was stolen away by high-energy physics to design the next generation lead the design of the next generation of particle accelerators. So we then had new leadership, Jay Marks, and now David Veinstein. We completed the initial interferometers. We installed the second generation advanced interferometers from 2010 to 2015, and we're just then ready to start our search with the advanced interferometers. But before I talk about that, I want to just remark that the Moscow State University group has been absolutely crucial to these advanced interferometers. Verginsky, Mitrofanov, Yachani, Khalili, Gorodetsky, Emelianenko, Strigan, and others in this group. They provided getting a little technical, fuse fillet fiber suspensions. They have been the experts in identifying what's called excess noise and how to control it. Discovered a number of problems that are huge problems that nobody had thought of, and figured out how we might deal with one's parametric instability. But above all, Verginsky, already in 1968, that's almost 50 years ago, he realized that however you detect gravitational waves, whether by this method or any other method, you must deal with quantum mechanical behavior of human-sized objects. In this case, quantum behavior of the mirrors that has the light bouncing back and forth between them. And the problem is that when the light measures where the mirror is, more technically, where the center of mass of the mirror is, fluctuations in the light power push on the mirror and change its position. And the more accurately you measure where it is, the larger these fluctuations are in the light power that change the position. This is a version of the Heisenberg uncertainty principle in quantum mechanics. And so in advanced LIGO, for the first time, we, as Brzezinski told us, we would have to deal with 40-kilogram objects that behave not according to the laws of classical mechanics, but according to the laws of quantum physics. It's an entirely new regime for physics. For the first time, the human-sized objects behave quantum mechanically. And under the leadership of Brzezinski, the Moscow State University group and my group at Caltech together have developed quantum non-demolition technology, we call it, to deal with this. So this just gives you some idea of the problems that had to be faced. On the theory front, I realized in the early 2000s, right after I wrote the scientific case, the description of the science we would do with advanced LIGO, to get advanced LIGO funded, I became so worried that we could not simulate the collisions of black holes or other sources of gravitational waves. So when we saw the signals, we would not be able to interpret them. To interpret the waves that we see, we must compare the shapes of the waves, what we call the waveforms, with the results of simulations. And these sources, colliding black holes, are very complicated. The only way we can know the wave shapes. On September 14, 2015, the advanced LIGO detectors were just preparing for the first search. The first search was going to begin in about 3 days. And the signal came in. Fortunately, the detectors were ready, but the gun, the starting gun, like at the beginning of a race, it had not been fired, but the detectors were ready. The signal came in, and it stretched one arm of the gravity wave detector and squeezed the other one, and then stretched and squeezed in this pattern. The pattern looked like this. This is the raw data. It was a very strong signal. Bandpass filter. All of the data above 350 hertz is removed because the detectors are noisy above that frequency. Below 35 hertz, the data are removed. Otherwise, this is the raw signal, unprocessed. This is what we saw in Livingston, Louisiana. What we saw in Hanford, Washington, you compare them, they are essentially the same. When the data were cleaned up, then compared with the computer simulations from the SXS project that I started, the simulations of the red, the gray, cleaned up observational data, beautiful agreement. And you then looked at what did the simulations say was happening with the source. Simulations tell us then these were two black holes. One is 29 times as heavy as the sun. The other is 36 times as heavy. They collided and merged. The final black hole was 62 times as heavy as the sun. 29 plus 36 is 65. Subtract 62. 3 solar masses are gone. Gone where? They're gone into gravitational waves. It is as though you had annihilated, destroyed 3 suns and turned them into gravitational waves. And this happened so quickly that the power that came off, the energy per unit time during the collision, was 50 times higher than the total power put out in light by all the optical stars in the universe put together. 50 universe luminosities in gravitational waves from 2 colliding black holes. It is absolutely phenomenal. And no electromagnetic waves. Although searches were made by our collaborators, nothing was found. 2 more gravitational wave signals were seen during our search. It lasted for about 4 months. one was absolutely firm, a 14 solar mass and 8 solar mass black hole, much smaller than the original one solar mass of energy and gravitational waves, about the same distance from Earth. And then a third signal that was weaker, so we're not 100% sure that this is a real signal, but we're almost sure. 23 and 13 solar masses, much farther away, 3 billion light years. This is the beginning of gravitational wave astronomy. Humans had never seen colliding black holes before, now we have. And now we can begin to explore the properties of these black holes in our universe. Looking toward the future, advanced LIGO detectors are not at the sensitivity they were designed to have. They're a factor 3 away from that sensitivity. And over the next approximately 3 or 4 years, they will be brought down to that sensitivity by very hard work by the experimental team. That's what has been happening over the last 9 months. The detectors were turned off, and the team has been working on removing the bugs, removing the noise from these instruments. The next search will begin in a few weeks and will last for some months, and then they stop and work hard again to try to clean up these interferometers. When we reach our design sensitivity, we will see 3 times farther into the universe. That means we see 3 times 3 times 3 larger volume, 27 times larger volume of the universe. So instead of seeing about two or 3 events in 4 months, we'll be seeing more like several a week or maybe even 1 a day in 2019, 2020. There will be future improvements. By 2030, we will be seeing many per day with masses less than about 1,000 times the mass of the Sun. By 2040, we should be seeing all of the black holes colliding in the entire universe, out to what we call a cosmological redshift of sort of 10 or so, out to the era when galaxies were first being born. So that is a piece of the future. But we will see other sources. We will see gravitational waves from spinning neutron stars, or pulsars as they're called, from black holes tearing neutron stars apart, from neutron stars colliding, from the cores of supernova explosions, which will teach us what causes a supernova explosion to happen, how it is powered. And there will be huge surprises. That is the most important thing for me, because this radiation is so very different from any radiation we've ever used before. There will be very big surprises. Now I want, in my last 15 minutes or so, I want to focus on just 2 pieces of science that we will do. Exploring black holes, I've already told you some about that, and exploring the birth of the universe. We will do much more than that with gravitational waves. But to me, the most interesting thing immediately in the next few years, or the next decade or so, is exploring black holes. And then a little bit later, say 20 years from now, exploring the birth of the universe. Let me begin by telling you that a black hole is not made from matter like you and I. Rather, it's made from warped space and warped time. It's true that black holes are born by the implosion of a star after it has exhausted the nuclear fuel that keeps it hot. But that imploding star, all the matter in the imploding star has gone inward, and it has become so concentrated that it created a black hole around itself. And then the stellar matter inside the black hole has been destroyed in what is called the singularity of the black hole center. It's gone. But the mass is still there. It's just not in the form of matter. The mass that pulls gravitationally on anything in its surrounding, the mass by which the 2 black holes hold each other in orbit around themselves, that mass is now living in the warped space and time of the black hole. It's just like if you take a bow to shoot an arrow, you pull back, you have to do a lot of work to pull back. You put that work, that energy into the bent string on the bow. And it came from your muscles, but it's now in the bent string in the bow. It's the same here. The energy is in the bent shape of space and the warping of time. And that energy, according to Einstein, is equivalent to mass. Mass and energy are the same thing. That energy of warping is the thing that, according to Einstein's equations, produces the warping. It is an object that holds itself together through its own nonlinear interaction, in technical terms. It's what you would call a solid. And this is the shape of the warped space around the black hole. If I take a rapidly spinning black hole and I take a two-dimensional surface through the equator of the black hole, and I look at the shape of that surface, I will discover that as I go closer and closer to the hole, the circumference around the hole does not decrease as fast as you would have expected. In order to visualize that, I imagine our universe, or this two-dimensional piece of our universe, as living in a higher dimensional universe. For those of you who saw the movie Interstellar, this is the fifth dimension of Interstellar. And so we see what the shape of space looks like as shown here. This becomes flat far from the black hole. The horizon of the black hole is here. That's the surface of the black hole. You fall through there and you can never get back out. It looks like a circle, but I removed one dimension. This is just through the equator of the black hole. If I put that dimension back in, what was a circle then becomes a sphere, or a flattened sphere, a spheroid. So the horizon is a flattened sphere, though it looks like a circle. The color shows you the slowing of time near the black hole. Up here, time flows at 90% of the rate that it does far away. At the yellow location, it's flowing at 10% of the rate that it is far away. At the horizon, time is slowed to a halt. It's not flowing at all. The arrows show you how space is dragged into motion by the spin of the black hole. It's like the moving air in a tornado. It moves fast in the core of the tornado, more slowly as farther out in the tornado. And so, similarly here, we call this dragging of inertial frames, but it is really very much like the air in a tornado. One of the things that I am very eager to do is to make a map of the warped space-time around the black hole, in the same way as we now have maps of the surface of the moon, maps of Mars, the surface of Mars, and so forth. How do you make a map? Actually, not with LIGO, not a very good map. We need a different gravity wave detector, and it's called LISA, the Laser Interferometer Space Antenna. It is a detector that is likely to fly around 2030. It's a mission of the European Space Agency. It used to be a joint American-European mission, but the Americans are not very good at keeping their promise. And NASA, the Americans, pulled out for financial reasons in 2012, and now the Europeans are doing this alone. The Americans want back in now, and the Europeans will let us back in a little bit, but it is truly a European mission now. It consists of 3 spacecraft that track each other with laser beams. The current plan is 2.5 billion kilometers between these spacecraft. That's a very big distance, of course. That's about 10 times bigger than the distance between the Earth and the Moon. And when the gravitational wave comes along, it pushes the spacecraft apart and back together again. And this same technique, as in LIGO, is used to monitor the gravitational waves. And because this has much larger distances, it looks for gravitational waves with much longer periods, much lower frequencies. It, in fact, is very much like radio astronomy. If you think of optical LIGO as being like optical astronomy, 10,000 times difference in wavelength of light and radio waves, 10,000 times difference of wavelength between LIGO and LISA. And correspondingly, instead of looking and studying black holes that weigh 10 or 20 or 30 times as much as the sun, LISA will study black holes that weigh millions of times as much as the sun. Giant black holes like the one that lives in the center of our Milky Way galaxy. Now, what way that we plan to map a black hole is this. You have a small black hole orbiting around a large black hole. And as it orbits around, it creates gravitational waves. It creates ripples in the shape of space around the big black hole. I'm going to show you the orbit of a small black hole from a computer simulation, but remove the warping of space. You won't see the space warp, but you will see what the orbit looks like. From a simulation, the other thing I wanted to do was say that a full map of the space-time geometry, the warp space-time of the big black hole, is produced as carried by the gravitational waves that come from the orbital motion of the small black hole. And you can understand why that's plausible. You can get the entire map out. If you just look at the orbit of the small black hole going around a fast-spinning big black hole. This is a simulation by Steve Drasko. Just watch the orbit. You've never seen an orbit like that in the solar system. You've never seen an orbit like that anywhere else in the universe. But this is what the orbit looks like. It's very complicated. And it explores the entire region near the big black hole, sending off gravitational waves that carry a detailed map. So we should be able to map the big black hole in the same way as space scientists have mapped the surface of Mars, for example. And what if the central body is not a black hole? For example, what if it's a naked singularity, like a singularity inside a black hole, but without a horizon, without anything hiding it? Well, again, you can do a simulation. This is a simulation for what is called a Manco-Novikov singularity. It's a solution of Einstein's equations found by Manco and Novikov here in Moscow some years ago. A simulation of the orbit is by John Dupree. Down close to the singularity, the orbit is chaotic. Farther away, the orbits are quite smooth and regular. But look at that chaotic orbit down near the singularity. Completely different kind of orbit. The map will look completely different. The gravitational wave signal is completely different. So we have a tool for not just mapping big black holes. LISA will be a tool for mapping whatever massive objects there are in our universe that have small black holes traveling around them. The other thing that is particularly interesting to me is studying the dynamics of the geometry of space-time when black holes collide. And we will do this and we've begun to do this, by comparing computer simulations with the gravitational wave observations. And I'm going to show you what we have already done for that first gravitational wave signal we saw. If I just go back to the simulations, the computer simulations done by this XSS team, it's Caltech, Cornell, and primarily Caltech, Cornell, and the University of Toronto, CETA, the University of Toronto. Here's what it looks like. You see the two black holes, the warp space, the color is the slowing of time, the arrows are the dragging of space into motion, and watch. I'm going to pause the movie as they are nearly ready to collide. And it's a huge wave, like this huge splash in a storm out at sea. Gigantic splash. I've just stopped the movie. Now let it go, and it dies out. That's what produced the gravitational waves. That's what released as much energy as annihilating three suns. And we have the observational data. We compare with the supercomputer simulations, and we have the movie. This is the first time that we have really seen how warped space-time behaves in a storm, with time speeding up and slowing down by extreme amounts, as you see in color-coded. The shape of space changing by extreme amounts, as you saw in the shape here. Finally, I want to talk about the birth of the universe and exploring it with gravitational waves. So we look out in the universe and look at radiation that comes to Earth. We're looking backward in time. The first gravitational wave we saw was produced 1.3 billion years ago. And if we look back as far as we possibly can with light, we can only see back to when the universe was roughly 100,000 years, well, really about 300,000 years old. Because before that, the gas in the universe was so hot and so dense that light could not propagate. No form of electromagnetic waves could propagate through it. It was opaque. Any photon of light that was produced would be quickly scattered or absorbed and lose all the information that it was carrying. So we astronomers make pictures of what the universe looked like when it was about 380,000 years old, not earlier than that. If we could see neutrinos from the hot gas in the early universe, neutrinos, I remind you, are fundamental particles that penetrate very, very well. They penetrate through the Earth just like gravitational waves do, but not through the early universe. We would see the universe as it was when it was 1 second old. But before that, the universe was too hot and too dense for neutrinos to propagate. Gravitational waves are the only form of radiation that penetrates so effectively that it can travel through the hot, dense gas at the earliest moments of the universe. So they are the only tool we have for observing the birth of the universe. Or, more precisely, the only tool we have for observing the first 1 second of the life of the universe. And in fact, I think that there is a lot of very rich physics and rich violence in the first 1 second of the universe's life. And I will give you 4 examples, and then I will finish. The first example comes from Leonid Petrovich Grishchuk, a dear friend of mine. A physicist, an astrophysicist here in Moscow in the early years when I came to visit Moscow at the Sternberg Institute at Daiish for much of his career. And Leonid Petrovich, or Leonid, is an informal American, I call him. He, in 1975, had a brilliant discovery. Using the mathematics of Einstein's relativity theory, he discovered or predicted that at the beginning of the universe, whatever came off of the Big Bang at the moment when time and space became real, they emerged from some sort of quantum fluctuations and at a time 10 to the minus 43 seconds. It took 10 to the minus 43 seconds, according to our understanding, for the universe to come into being. Whatever kinds of gravitational waves came off of there, he discovered would have been enlarged, amplified by a huge amount in the earliest moments of the universe's expansion, what today we call inflation, through what is called a parametric amplification. the mathematics is beautiful and compelling, and although it went completely against what everybody believed at the time, the great experts immediately accepted it. And what Ionia presumed is that what came off the Big Bang is just the minimum amount of gravitational waves you can have according to quantum physics, what we call vacuum fluctuations. And assuming that, he found that you could get enough amplification that you could have gravitational waves strong enough that it might be possible to detect them. He called it primordial gravitational waves or primordial gravitons. And in fact, as I will describe, we have two different ways over the next few years, next several decades, by which I expect we will see these primordial gravitons. The first is these gravitational waves travel outward after being created or amplified by inflation. And at the moment when photons first can start to travel freely toward us, they interact with the hot gas and they place on the photons through scattering off of electrons and hot gas. They place a pattern of polarization on those photons, and those photons today are in the microwave frequency band. So it's a polarization of the cosmic microwave background radiation. And so cosmologists are searching for that pattern. They have found it, but they have some noise in their data that they have to get rid of and solve before they know for sure what they are seeing. But this is going to be the first realization of exploring the birth of the universe with gravitational waves. Not with LIGO's gravitational waves that oscillate at about 100 oscillations per second. But with gravitational waves of a very long wavelength, very low period, that have placed a pattern on the sky in this microwave radiation. So this is a different frequency band, completely different technology. I've told you now about 3 different kinds of great gravitational waves we will see. LISA, the analog of radio astronomy, LIGO, the analog of optical astronomy, and this wonderful primordial gravitons with very long wavelengths. There's a 4th one that I won't describe, but within the next 20 years, we will have 4 different frequency bands in which we see gravitational waves. It's as though we had opened up the optical window on the universe, radio astronomy, X-ray astronomy, and gamma ray astronomy, all in 20 years. That's what we will have with gravitational waves. In the 2040s, we expected a follow-on mission to LISA, involving several versions of LISA traveling around the sun in interstellar space, with each one using light beams to measure the spacecraft. That will have far better sensitivity than LISA, and it will also see Grishchuk's primordial gravitational waves, but now in a frequency band that is 10 to the 14 times higher frequency, 100 trillion times higher frequency than the microwave background. And to see what was happening in the Big Bang in these enormously different frequencies was really the beginning of getting a rich exploration of the birth of the universe. Second example, when the universe was 1 trillionth of a second old, the electromagnetic force was created. Earth, that the universe was so hot that the electric force and magnetic force were unified with the weak nuclear force. As the universe cooled, according to theory, this very solid theory, these forces came apart, and the laws of physics as we now know them came into being. The electromagnetic theory that you study in your classes, it came into being. The electromagnetic equations came into being, the Maxwell equations, when the universe was 10 to the minus 12 seconds old. It is fairly likely that this happened inside bubbles, like raindrops condensing out of water vapor. And the theory says that these bubbles, with the electromagnetic force existing inside, and not outside. These bubbles traveled outward, expanded at the speed of light, collided, and produced gravitational waves. And then the universe expanded from then until now. These gravitational waves were stretched so that today they are in the frequency band of LISA. And so LISA will search for these gravitational waves to watch the birth of the electromagnetic force when the universe was 1 trillionth of a second old. LIGO can see a similar phase transition, we call this, when the universe was 10 to the minus 22 seconds old, but we have no idea what the physics was when the universe was that early. But LIGO has the capability to explore the universe at age 10 to the minus 22 seconds. There are things predicted to exist called cosmic strings that are sort of like cracks in the shape of space. The circumference around a cosmic string is less than pi times its diameter. And these cosmic strings can get plucked. They can have a bend, a kink on them, and if the kink travels down the string, it throws off gravitational waves. We know that these cosmic strings are thought possibly to have been created in the Big Bang. LIGO is currently searching for them. We know from theory the shapes of the waves, and we're searching for waves that have that shape. Finally, our universe might have been born as truly a membrane that lives in higher dimensional bulk, as we call it as physicists. It might have been born like a sheet of paper, crumpled up, as I show here. But there's tension in our universe. Our universe is like that two-dimensional sheet of paper. And when this part of the universe and that part of the universe discover each other, as the universe is expanding and aging, discover that there is a bend in the paper in between them, that bend quickly straightens out because of the tension in our universe as it lives in the higher dimensional bulk. And so the universe becomes like this, and that straightening out produces gravitational waves that travel through the universe. This is very speculative. Probably not true, but it might be true. It's an example then of the kind of surprise that gravitational waves may bring us. And so, to conclude, gravitational waves will be a major tool for astronomy into the next century and beyond, into the following century, and perhaps beyond that. Thank you. And it's because, for those who are physicists, conservation of energy is tied to something called time translation symmetry, which you do not have in a dynamical space-time. For example, when two black holes are colliding. And so energy conservation works sometimes, but not always in general relativity. This is yes, then, but the answer is not yes. So why were primordial gravitational waves not absorbed? Let me answer that by describing the problem of detecting the gravitational waves. The power of the gravitational waves that we first detected was huge. if we had that much power coming at us, or energy flux coming at us in light, it would have been brighter than the full moon, but concentrated in a tiny, tiny spot. It's unbelievably bright. The flux the same more from the full moon. And yet it required $1 billion and 1,000 people and 50 years to detect those waves. Why? Because those waves do not interact with matter strongly at all. They travel through matter, and it's extremely hard for matter to experience it. And similarly, that's why they can penetrate through the hot, dense gas at the earliest moments of the universe. They're just very, very penetrating. It's their property, crucial property, which is wonderful for being able to see things that you cannot see in other ways, but it is a real problem if you're an experimental physicist wanting to discover them. So I will tell you a story, and then maybe we should quit. In 1978, when I had been working on gravitational waves for 10 years, the first 10 years out of 50 years, we had a conference in Seattle, Washington, to discuss the future of this field. And almost all the people in the field were there. There was about 30 people, maybe 40 people from all around the world, including Moscow. And we looked at all of the sources of waves that we knew about, estimated their strength, and came to the conclusion that the strongest the waves were likely to be, the wave that we first detect, was 10 to the minus 21 for this strain, the change in distance between mirrors divided by the separation. And so we had t-shirts made up, like this t-shirt. It said 10 to the minus 21 or bust. So that's an American phrase, 10 to the minus 21 or we have completely failed. We must make 10 to the minus 21. And I will tell you, the strength of the first gravitational wave that we found was 1.0 times 10 to the minus 21. So this is a wonderful gift. Thank you very much for everything. Okay, so how can you prove that you measured a change of space but not a change of the Earth's size? The reason we know that what we're seeing really is due to a stretching and squeezing of space is this, that these mirrors, as they hang from overhead supports, they are inertial. We're looking at motions at a frequency of 100 hertz, 100 times higher frequency than a pendulum swings. So they really are inertial. They are riding on space. And so how do we know that they really move by this amount? Well, the experimenters calibrate these instruments. They apply an electrostatic force to the mirrors and move them back and forth by a known amount, because they apply a known force. Electricity is very well understood. They apply a known force. And then the signal goes through all of the instrument, the computer, the data analysis, and to the experimental team. This is done about once a year as a test of the experimenters and the detectors. Nobody knows that they have done it except 3 people who are in charge. And they will move the mirrors by just the amount that they should be moved. If the gravitational waves are from two black holes in that direction, particular masses and spins for the black hole, and they do it on both the detector in Washington and the one in Louisiana, with a time delay corresponding to that direction. So the morning when we got the discovery data from the computer, I looked at it, and everybody else on the team looked at it and said, this has to have been put in by that team of 3 people who were supposed to test whether or not we know what we're doing. Well, it turned out they didn't put it in. And so one of the reasons that it required 5 months to be sure that this really was a gravitational wave was it was necessary now to go in and look at all the places that if this had been done by hand, there are many data channels where there is certain kinds of noise or signals that tell you this was done by hand. The data channels, nobody has been able to figure out how to remove this secret from those data channels. So intense studies were done. But this calibration is crucial to knowing that the instrument is working the way that it is. And that's what gives us complete confidence in this.
There is a question which is required in the next lecture. What do you think about dark matter?
I think that dark matter is a wonderful mystery. It's probably some sort of fundamental particles that interact briefly with ordinary matter, but we don't know for sure. But I think it's a high probability. When we do understand it, that will be a major discovery about the laws of nature. What do I think about Elon Musk's SpaceX? Is it possible? Well, SpaceX exists. It's a question, do I believe that by the middle of this century he can have a colony on Mars? So Elon Musk is a personal friend. And before he announced that he had a goal of putting a colony on Mars, I had a long conversation with him at a party where we were both a little bit drunk. And he was telling me this, and if anybody else had told me this, I would have been very skeptical. But he has a remarkable track record that is just amazing of doing the things that he says he's going to do. And so I think that if he puts a huge amount of effort into it and convinces investors to do the same, that he probably can achieve what he wants to do. But it's based only on personal faith in a person who is an absolutely amazing person.
The next question in Russian, I translate. How to define distance to merging black holes?
So, when we saw these 2 black holes spiral together and merge, we were able easily to measure 2 masses. First, from the rate at which the black holes move together, that is, the rate at which the frequency of the waves became shorter and shorter, we could directly compute a certain combination of 2 masses. From the frequency at which the signal ended, that told us basically how big the final black hole was. We could determine the mass of the final black hole. And with those 2 masses, we had much more data than that, but those 2 masses were enough to tell us approximately to within 20% how strong the waves would be at any distance we might choose from the black hole binary. And LIGO measured how strong the waves actually were, and we could then see just how far away we were, and it's 1.3 billion light years. So it's a very clean measurement. It comes because we really understand from computer simulations, yes, but reliable computer simulations, we truly understand what the signal is we can get the masses from the shape of the signal, and we can then compute how strong the wave should be and deduce thereby the distance.
Last question.
Can we create a scenario machine to detect wormholes using LIGO data? So I think it's very not likely that wormholes can exist. I could be wrong. I tried very hard to figure out whether the laws of physics permit wormholes, and I failed, and so has everybody else. But there are strong indications from the laws of physics that wormholes cannot really exist. If I'm wrong, then it would be very interesting to look for gravitational waves from binary wormholes. But for that, we need to know more about the wormholes than we do. Black holes are remarkable in that if you just know two numbers, how heavy the black hole is, its mass, and how fast it's spinning, you can then compute everything else there is to know about the black hole. And so we can compute these gravitational wave shapes with very high confidence. Wormholes, if they can exist, they have a lot of freedom in their shapes, and as a result, we cannot make reliable predictions for the waveforms when the wormholes would get close together. And so I'm not optimistic, but it is certainly a problem we're working on. We're putting effort into to try to understand if wormholes are allowed, to understand more reliably what their shapes are and what the gravitational signals would be.
Thank you very much, Kip.